Welcome to The Explainer. Today, we're diving into something pretty huge. Why are physical machines, we're talking cars, robots, drones, demanding this endless supply of more and more powerful computer chips? Well, the answer isn't just about making things faster. It's a story about the unforgiving laws of physics.
All right, let's get right into it. To really get a handle on this, we're not going to start with some sci-fi robot. Nope, we're starting with something way more familiar, a car, just driving down the highway. What does that machine actually have to see and think about every single moment just to keep you safe?
You know, a modern self-driving car is basically a rolling supercomputer. It's not just looking through one pair of eyes. It's taking in information from a whole suite of sensors, like up to a dozen high-res cameras, radar that can see straight through fog, and LiDAR, which uses lasers to paint this incredibly detailed 3D map of the world millions of times a second. It is an absolute flood of information.
And here is the absolute kicker. All of that data, from all those different sensors, it has to be collected, understood, and then turned into a decision in less than 100 milliseconds. That's literally faster than you can blink. So why does it have to be so ridiculously fast?
Well, because this isn't about loading a web page a little faster on your phone. This is about physics. And in the real physical world, delays have direct and often irreversible consequences. So this isn't just some tech challenge. It's a life or death calculation that is governed by the basic laws of motion.
And this is where it gets really real. This slide translates that tiny number, 100 milliseconds, into a terrifying distance, almost 3 meters. That's the length of a small car that you travel completely blind. This is the absolute core problem of what we're calling physical AI. There is just no room for error when your software is controlling actual atoms.
And this intense, high-stakes need for near-instant processing, it isn't just happening on our roads. Not at all. It's really the defining challenge across at least 3 massive, world-changing arenas where AI is moving off the screen and into our physical lives.
So arena number 1, of course, is the multi-billion-dollar moonshot of autonomous driving. You've got companies like Waymo packing vehicles with more than 29 cameras, while Tesla is using its fleet of millions of cars to vacuum up billions of miles of real-world driving data. The complexity is just staggering, and the safety stakes, well, they couldn't be any higher.
Second, there's this quiet revolution happening inside our warehouses. I mean, Amazon now operates an army of over 1 million robots. And these aren't just dumb machines following a line on the floor. They are navigating chaotic, constantly changing environments in real time, coordinating with hundreds of other robots, and using some pretty advanced AI to learn how to pick up millions of different items they've never even seen before.
And third, the sky itself. Autonomous drones are completely changing everything from package delivery and bridge inspections to national defense. We are talking about systems where a single pilot can command a whole swarm of 20 drones at once, and each one of those drones is making its own critical decisions on the fly.
So how on earth do these machines process so much stuff so incredibly fast? Well, the answer isn't one single superbrain. It's actually a really clever two-part system. It combines lightning-fast reflexes with a deep, almost infinite memory. Think of it like this. On one side, you have Edge AI. That's the computer inside the car, or the robot itself. It's the fast, local reflex system making those split-second decisions. Then, on the other side, you have Cloud AI. That's the massive data center, the collective brain where all the deep learning happens on these giant clusters of GPUs, analyzing data from the entire fleet to get smarter and smarter.
And Tesla's famous data flywheel is the perfect example of how these two parts work together. You've got their 5 million cars on the road acting as this giant network of data collectors. That data gets uploaded to the cloud to train a better AI model. Then that smarter model gets pushed back out to the entire fleet. The cycle just repeats, getting faster and smarter every single time. It's a brilliant feedback loop.
But here's a huge problem. What about the scenarios that are so rare and so dangerous that you can't just wait for them to happen in the real world? We're talking about that 0.1% of events that are the most critical. You can't exactly train your AI for those by crashing cars on purpose.
This quote, which comes from BMW's work on planning its factories, just nails the solution. If the real world is too risky or too slow or just way too expensive for training, you build a perfect digital copy of it. You build a simulation. These digital twins are absolutely essential. They let companies safely test millions of dangerous what-if scenarios, like a child running into the street or a sudden tire blowout on the highway.
They can train an AI for billions of virtual miles, getting it ready for things that might only happen once in a million miles of real driving. This isn't just a nice-to-have. It's a requirement for safety certification. And guess what? It takes enormous GPU power.
So you can see how all of this technology starts to build into this really intense global competition. Because when the performance of your AI is directly tied to safety and efficiency, the company, and for that matter the country, with the most compute power, they have a decisive, almost existential advantage.
In self-driving, this whole thing plays out as this fascinating strategic duel. On one side you have Tesla, betting big on a vision-only system, using its massive fleet to gather data. And on the other, you have Waymo, betting on a super expensive but highly redundant system that's packed with LiDAR, prioritizing absolute safety right from the start. Two totally different philosophies, and both demand a colossal amount of computation.
And this race is absolutely 100% global. In logistics, you can see this direct competition between America's Amazon, with its focus on human robot teams, and China's JD.com, which is pushing hard toward fully autonomous warehouses, treating it as a national strategic priority. Falling behind here is simply not an option.
So here's the crucial point. All of these forces, the demands of physics, the need for mountains of data, the intensity of global competition, they all lock together. And they create this unbreakable, accelerating cycle of demand for more and more powerful hardware.
First off, just think about the stakes. Unlike a software bug that just makes your phone crash, a bug in physical AI has direct, irreversible consequences in the real world. When your errors are measured in actual lives and injuries, good enough is never, ever good enough. The drive for more safety automatically means a drive for more performance. Second, there's the competition. For these companies and for the countries they operate in, this has become a full-blown technological arms race. Having superior AI in logistics, in manufacturing, in defense, it's a massive economic and strategic advantage. You simply cannot afford to fall behind.
And finally, the technology itself is just exploding in complexity. To handle all this real-world chaos, the AI models are getting exponentially larger. We're talking 10 times bigger than the previous generation. And that requires a similar exponential leap in the compute power you need to train them. The software is demanding more power, just as much as the physics is.
And this brings us to the ultimate takeaway. For any company that's competing in the world of physical AI, buying the next generation of chips isn't just some minor optimization to get a little bit faster. It's not a choice. It is fundamental to their very survival. It is, as the slide says, an existential necessity.
This relentless cycle is fundamentally reshaping our physical world. It's tethering our future progress in everything, from transportation to manufacturing, directly to the pace of innovation in semiconductors. And that leaves us with a pretty powerful and provocative thought to chew on. Thanks for joining this explainer.